You're like this height. I don't know. Why are you trying to
He's slow. Stay calm.
Hey.
Oh, God.
3. We're starting.
You think that clock is glow in the dark? We should find out.
It looks pretty glow in the dark.
It looks like, yes.
Dudes, time to start. Okay, trajectory motion, otherwise known as 2D kinematics. All right, here's the deal. In trajectory motion is important for us because on Earth we have a hard time escaping gravity. And so when things fly through the air or move about under the influence of gravity, particularly when they're only under the influence of gravity, okay, neglecting air resistance, then we're going to have this particular motion all the time, okay? So we study it. All right, here we go. If you had a strobe light going, okay, strobe, flash, 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 all right? And you had a person that was moving to the right at a constant velocity, okay? What would they look like? What would it look like if you saw them with a strobe? The first flash are here.
Appearing at equal intervals.
Yeah, they'd show up here, and they'd show up here, right? And so forth and so on, right? Okay, so if we did that for an object that was like rolling across a table where we have no friction or very little friction, it's going to look like this. There, 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 there. Hey, come on. There, there, there.
Okay.
And keeps going. Okay? Every second it moves the same distance.
It's pretty equal. Pretty nice.
Thank you. I appreciate the vote of confidence.
Good job.
All right, now. But what would it look like if you, say, took your little brother and you had the strobe going, and you took your little brother and you threw him into the air? What would that look like? Besides funny, if they're right here after the first flash, where would they be after the next flash?
A little bit closer. A little bit closer.
And then eventually stop, right?
Because they're slowing down.
So they'd be up here, and then they'd be less and less and less, and eventually stop, right? And then on the way down, what would it look like?
The same way going up.
Same, but in the opposite direction, right? Okay. So here's the deal. What if you did both at the same time? You took your little brother and you threw him across the room.
It'd still be the same. Might be the same.
It would be adding.
Wouldn't they go up and come back down?
Yeah.
And wouldn't they move across the room at a constant speed?
Assuming that's how you.
Because is there anything to slow them down if you move them across the room?
No.
Unless he gets something.
Air would be our only thing, right? And if air resistance is small, then we could neglect it, okay? So here's where you would start, and then after one flash of the strobe, you'd be here. Then after another flash of the strobe, you'd be here. And then another flash, you'd be here. And then another flash, you'd be here. And then here, coming back down. And then here. And then here. And then here.
That's a good drawing, Mr. Ray.
Why, thank you. It's only taken me
Wow.
That is kind of
You're like a human compass.
north.
No, like a compass that you draw circles.
Ah.
Yes.
That's a protractor.
No.
That's a compass.
All right, so, okay, here's the deal, everybody. All right, the deal is that what we have in trajectory motion is we have motion this way. We have motion this way where we have no acceleration, okay? The object just continues to move at a constant rate. And in the up and down direction, we have acceleration. The acceleration is down, and it's the same all the time. So, in this direction, in the y direction, we have an acceleration that equals g on Earth. Okay? And that is downward. And it's constant. In the x direction, we have an acceleration that equals 0. Okay? So let's take a look at what happens to our three equations. All right, so let's take a look at our equations that we get as a result of this. Okay, our three equations, what are they? We'll start right here. X equals x naught plus v sub 0 t plus at squared. All right, what's our next one?
V equals V naught plus AT.
Okay, and what's our last one?
V squared equals V naught squared plus 2a times
D minus.
Okay, remember x minus x naught is the distance, right? Okay, x is the initial position, x is the final, x naught is the initial position, final position. All right, so there we have it. But wait.
Which one?
Acceleration is 0. 0. 0. And 0.
0.
So what does the last equation tell us?
That's why I thought
Well, the velocity equals the final velocity.
Okay, so the last equation tells us the velocity doesn't change.
Same thing with the second one.
And the second one tells you that same thing, right? Okay, and we should know that already because the acceleration is 0, right? That's what that means. The velocity is not changing, right? So we can throw these two away. Actually, I'll just leave this one up here to show you that the x velocity and the final x velocity are the same. Velocity never changes. Okay, what does the next one or the top one tell us?
Precision is this initial precision plus the velocity. Initial velocity.
Yeah, it's initial position, our final position is our initial position plus velocity times time. By the way, that's the same thing as saying velocity equals the change in x over the change in t, because remember, that's x final minus x naught over t, right? That's this equation right here. Okay? So, in the x direction, all we really have is that, assuming we start at 0 position, it's just our velocity times time tells us how far we've gone. Right? That's it. That's all we got. So the x direction is easy. Easy, easy. Easy peasy lemon squeezy. That's correct. Now, let's look at the y direction. In the y direction, what are our equations? Well, they're y equals y naught plus v naught squared, vy naught squared, not squared, vy naught times t plus 1/2 g t squared. This is the same equation we already knew, right? All we're doing is we're just plugging in y's for x's, right? It's the same as x equals x naught plus v naught t plus 1/2 at squared, except we're plugging in y's, and instead for acceleration we're plugging in g, right? And that's it. So there's our first one. Our second one is vy equals vy initial plus gt, right? And our last one is vy squared equals vy initial squared plus 2g y minus y naught. All right, and that's it. Now, can we do anything else to simplify those, or are we stuck? We're stuck. That's we plugged in what we can plug in. That's it. Did I write them all correctly? They look okay? Okay. So in the y direction, we have these three tools. In the x direction, we only have this one tool because that's all we need. X direction is easy, easy. So, so all you have to do is you have to remember, very, very important, that the x stuff has to stay with its own x stuff. And the y stuff has to stay with its own y stuff. The only information that can pass between the two is time. And what's special about time? It's a scalar. It's Since time is a scalar, it can appear in either equation. But since this is x vector stuff, you got to keep all the x vector stuff together, like we talked about last time. And all the y vector stuff has to stay together. And that's the key. If you can do that, you're going to be in great shape. So, trajectory motion. There are really only 3 types of problems. Okay? Type of problem number 1. Number 1, because here's the deal. All trajectory motion problems, they all are this shape. Every last one of them. So if you drive your car off a cliff, you begin here with your car, and you drive off the cliff. And so you will be this half of the parabola. Okay? Or let's say that you have trouble getting a job after college because you didn't study enough, and so you take a job at the circus. And you're that person they put in the cannon. So here's our cannon, right here. And this is you being launched. And you're happy because it's fun. And you only have to do this twice every other Saturday.
Right.
All right? And you get launched with a velocity. And you go all the way over here and you land.
You hit the car at the top. And then
No, hopefully you don't hit the car at the top. And you land over here in the net. Yeah, you land in the car, then drive it into the net. Very nice. Okay, so you launch here and you land here. That's our second type. Okay, where you launch and land at the same height. And then there's all kinds of other ones that fall somewhere in between. There's the problem that, say, this is you down here and you're shooting a basketball. You shoot here, and you start with your basketball right here, and you launch it up this way, but then you shoot it towards the hoop, which is here. Okay? Or let's say that instead of driving your car off a cliff, that was not nearly as dangerous and exciting enough for you, so you launch your car off a cliff at an angle. So you could launch your car up starting here and then land down here if you want, right? You could do that. Or let's say it's Christmas time and you're delivering presents and you're Santa and you slide off the roof. You trip and slide off the roof. So you would start right here and you would land down here, right? So you'd start there and land here, correct? Okay, all of those are the same parabola. Okay? The only difference is how tall or wide the parabola is, okay, depending on your initial velocity, okay, and your initial angle. That's all the difference it makes. All of those are the same parabola, okay? So if you're in the Olympics, parabolas all over the place, okay? If you're a gymnast, you're bouncing around in parabolas. If you're a high diver, you're diving off the diving board, but your parabola is very steep usually, right? You go almost straight up and straight down, almost. Right? Straight up, straight down is not good because then you land on the board, right? Okay. So if you happen to not like your neighbor and you launch water balloons into their yard, it's parabolas, right?
toilet paper.
Or toilet paper. As long as you don't have too much air resistance, right? As long as you don't have too much air resistance, it's all going to be the same parabola. Now, if you have air resistance, how's it going to be different? Well, we'll study that in physics. So yeah, what happens is it slows you down, you land over here. And so you start on a parabola path, but you end up not in a parabola. You'll fall short, okay? So any ball sports, parabolas all over, okay? All right, so let's figure them out. Let's start with problem type number 1. Number 1, driving your car off a cliff. It's been a tough day in class in physics, and you wanted to try out your newfound skill in parabolas. So you take your car, and because you're the smarter of the two of you and your friend, you have your friend drive the car, and you put the pillows down here.
Mr. Bruin, I think it would be more interesting if Mr. Carter was taking a student off of a cliff.
All right. So let's do this. Let's say that you tell your friend, look, I'm going to place this big mattress down here at, how many meters? How many meters do you want?
15.
15 meters?
30.
So now you have to find out how fast you have to go.
Yeah,
on the spot.
how tall is our cliff?
50.
50?
Yeah.
Oh, wow. 50 meters.
Yeah, you have
They got some Tempur-Pedic mattresses.
I know, like big
Man, you're going to need a couple mattresses then. Let's put another one on top.
Subtracted meters.
I mean, you have to increase the height so it's 50 minus the
Now,
height.
okay. Yeah, that's right. If this is, yeah, you don't want to land in the middle.
What sleep number should we set the bed?
That's right. We're going to put this on sleep number 0 and make it very soft. Soft landing. Okay, so here we go. Okay, what velocity should your friend drive off the cliff in order to land in the mattresses? Go. Okay.
I don't have a calculator.
Uh-oh. Here's our first dilemma that's been brought up. Okay, look. We have x equals x naught plus v naught t. Where is the person starting? 0. We're looking for this, right? We know this is 15. 15 meters equals v naught times t. Okay, dilemma. What's t? Okay, the answer is we don't know. But we have to find it out. Can we find out the time in the x direction? Is there anything else we can do?
Time in the y direction.
All right, so here's the deal. We have x stuff and we have y stuff. The x stuff that we know is that we're going to start at 0, we're going to land at 15, we hope. We know the acceleration is 0, that's it. That's all we know. And we know our only equation over here is x equals x naught plus v naught t. That's it. So we can't do anything else with this one. So over here, what do we know?
Y initial is 50.
Y initial is 50. What's y at the end? 0. Okay, now, I don't know that you all realize this, but you just set the sign convention. Which way did you say is positive? Now wait a minute, in the y direction. In the x direction we called that positive. We called up positive, didn't we? We just set positive as up. Could we have set positive being down? We sure could if we wanted to. If so, we would have said that this is 0 probably, and we land at 50. And then down would have been positive. It doesn't matter which way you choose to do it, but this is important because that makes our acceleration negative 9.8 meters per second squared. Very important. Because if you put positive here, then you're in trouble. Anything else we know in the y direction?
No.
One more thing.
Initial velocity.
Vy initial equals?
0.
0. How do you know?
Oh, because you're not going up.
Because when you begin, you're neither going up or down. You're at the very top of the trajectory, right? The very top of the trajectory. Now, knowing this information, can we find time?
Yes.
Yes, we can. And it looks like this. Y equals y naught plus v y naught t plus 1/2 g t squared. But I'm landing at 0. This is 50. That's 0. Our initial velocity is 0. And then I get a minus 4.9 t squared. So 4.9 is from 1/2 of 9.8. So you'll see a 4.9 sometimes pop out of the equation. That's where it comes from. Okay, so t is going to be equal to 50 divided by 4.9 square root. Now, if I'd have kept that in symbol form, which I'm going to do right now because it comes in handy. That comes in handy if you do this. If you call this h, you end up with 0 equals the height of the cliff minus 1/2 gt squared. If you solve for t, you get 2h over g square root. Now this little deal right here comes in handy sometimes. Okay? This is good if and only if the initial y velocity is 0. So like for instance, can I use this equation to find how much time it takes for this to get to the ground?
Yeah.
Let me show you again. Did you catch that?
No, I didn't.
One more time?
Nobody's
What about this one? Can you do it for that one?
No.
No, because the initial y velocity is 0. How about this one? Yes?
Yeah.
How about this one?
No.
No. Oops.
Wow. Busted.
All right, so as long as it has an initial y velocity of 0, so either dropping it or launching it horizontally, right? Okay.
You have more markers left. You can keep going.
Didn't quite get it? Try it again.
Into the trash can.
Oh, over the trash can.
Never seen in the finals. Unlikely.
Okay, so what's our time?
3.19. Yeah.
3.2-ish
19 seconds.
seconds. So now, wait a minute. Time is 3.2-ish seconds. So I can pass that over to this column now. Because it's a scalar. And now can I find how fast?
Yeah.
Sure I can. I plug that in here. And how fast must the person be going? About 4.7 meters per second. 4.7 meters per second. And they will land nice and soft and cushy on our sleep number bed. Okay? There you go. Now, could we have asked that the opposite way? Could we have said, hey,
Where to place the mattress?
yeah, where to place the mattress? And ask for X instead. Sure.
It's 15.
It's 15, very nice. That was very quick. How'd you do that?
I did all that in my head.
You did all this in your head, so you found the time,
Yes.
and then once you found the time and you knew the velocity, you found the distance, right? Okay, really they can only ask that question one way or the other, pretty much. There's really no other way to ask it. This question shows up on the exam all the time. Okay, you ready? Here's how it shows up. Okay. Car driving off cliff. A diver dives off or runs off a diving board horizontally. Same problem. A ball is thrown off of a cliff. It could be like this, though. It could be like this. You've got a ball on the end of a string that you're spinning around. The ball's spinning around the end of a string. When it reaches the bottom, the string breaks. Voila. Trajectory motion problem. Hey, what if it broke at the top? Voila. Trajectory motion problem. Hey, what if it broke right here?
Voila.
Voila.
Straight up.
Oh, that's a one-dimensional problem, right? Straight up and straight back down, right?
I get that one.
Oh no, what if it breaks right here? Uh-oh. Now we have a different type of trajectory motion problem, right? Okay, another type. Do we still have that mass on the end of the string around here somewhere? All right. So you got this problem. When we get into circular motion, okay?
Let me like it when it breaks off. Oh my God. We're going
You'll be
down.
laughing when it breaks off. Hang on, where should I let
Oh
go?
my no.
There.
Okay, let's measure their distance and the
That's right.
height, so we'll find that.
Okay, now let's say that I'm spinning this around like this. We're in circular motion. So I'm spinning this around, and then right there, it breaks off. Right there. See it? Right there? Right there.
It would go off that way.
All right, right over there, it breaks off. Wait a minute. When it breaks off, what kind of motion will it be?
Trajectory.
Which one?
Breaking from the top going downwards.
The car driving off the cliff, right? Because it was going horizontal, right? So when the string breaks, it'll take off with a horizontal initial velocity, right? All right. So that type of problem shows up all over the place. Another place it'll show up is you got a roller coaster. Roller coaster. And the car breaks, the track breaks, and the car takes off.
Oh Lord.
Oh, that would be awesome.
Okay.
What is this, an AP test grade?
They had one time where I believe Tarzan was swinging. Tarzan was swinging from a vine, and at the bottom of the vine he lets go. And so if he swings on a vine at the bottom and he lets go, then it's this problem again, right? Okay, so this problem will always show up in multiple choice and probably the free response. Okay? So this is the easiest one of the batch. And this is our special equation to find time, the time to fall, but it's only good for horizontal launch or dropping with no initial velocity. All right, so let's go to a little bit harder one. Okay, let's talk about our circus problem. You're at the circus. You're going to launch yourself out of a cannon into a net. You should be excited.
How about with some fiery hoops that you have to go through?
Ooh, you mean like Archery of Doom?
Yes.
Can you solve that problem?
It's right here. Okay, you're going to launch yourself with a velocity. Here's your launch angle. Your launch angle is theta. All right? You're going to go like this out here, and you're going to land over here in your net. And your net is at the exact same height. This is sometimes called a range problem, because this distance is generally referred to as the range if you launch and land at the same height. Okay? All right. Whenever we have a problem where you launch at an angle, all right, everybody ready? Write this down. The very first thing you should do when you have a problem where it launches at an angle.
Just panic.
No, do not panic. Remain calm. That's the first thing. Skip it. No, do not skip it. The very first thing you always do, whether they ask you to do it or not, is to take the velocity and do what with it? Break it into its separate components. Absolutely, positively split it into two pieces. Into the Vx and the Vy. That's correct. So you must split it into Vx, and that will be the initial, and Vy initial. But do I really need to put initial velocity here?
No,
Because it's always the same, right? It's never going to change. So this Vx, given this theta, because usually they give you the angle with the ground. They don't have to. But if they give you the angle with the ground, this is going to be V, what? Sine or cosine?
Cosine.
It's the angle, it's the part down here, right? It's the adjacent. So cosine theta, and that means this one is going to be V sine theta, because it's going to be the vertical part of my triangle over here, right?
Yeah.
Okay, so let me draw it just in case. There's my Vx, there's my Vy, and there's my total V, and there's theta. So this is going to be V sine theta, and this is going to be V cosine theta. All right? That's the very first thing you have to do. All right, so let's do a little mathematics here. How do I figure out how far it's going to go? The range. Ooh, I'm going to need the time, aren't I? Okay. Because in the x direction, all I know is the x range is going to equal the x velocity times time, right? And I know the x velocity is v cosine theta, correct? But I still need to know the time. So I got to find time. If I can't find time in the x, what do? Find time in the y. Okay, so, all right, riddle me this. Which one of these am I going to be able to use to find time?
The second one.
The second one, what?
Because you know Vy is going to be the opposite of Vyo, right? Negative at the end.
Ah, okay. Does everybody catch that? Here we go. This velocity right here, the x velocity, x, always stays the same. The y velocity, on the other hand, is up, and a little up, and a micro amount up, and then my velocity at the top is 0. My y velocity at the top is 0, correct? And then it turns around and goes the other way. Vy, and Vy. And the y velocity over here is the same as the y velocity over here, they're just in opposite directions. Okay? Now there's a couple ways you can do this. One way is students will say, look, I know that the landing velocity is going to equal the launch velocity if I land at the same height,
Or you can do that.
but it's going to be in the opposite direction.
You just calculate gravity.
And so you would just figure out, and you know g is going to be 9.8, right? So you can find out the time that way.
Or you can do that at the top.
Yeah. So what some students will do, because it's math is a little bit easier, is they'll go from here to the top, or they'll go from the top down to here, it doesn't matter, and find the time, and then what do you have to do with it? You got to double it to get the total time. That works too. All right? So let's do, I'm going to do the one that you're less likely to try probably. V equals V naught plus GT. Those are y's. And I'm going to do the landing velocity will be negative V sine theta. And the launch velocity is V sine theta. They're opposites of each other, right? Plus, will it be plus G or minus G? Minus G because it's downward, right? So my time is going to equal 2V sine theta over G, right? The board looks what? Thank you.
Yeah, how do all your markers work? Like, all the other teachers have like crappy markers.
Work.
He adds.
I keep my markers hydrated. That's right. They're on illegal substances. All right. All right, is that correct?
Yeah.
Did I make a mistake, or is that correct?
No, that's right.
Is that correct? All right, what do I do with that time? I plug it in down here. And when I plug it in down here, I will get V cosine theta times 2V sine theta over G. And when I multiply that together, I get a V squared, and I'm going to have a 2 sine theta cosine theta over G. That is a property. Does anybody know what that 2 sine theta cosine theta equals? Very good. It's a sine 2 theta.
That's what Chris said.
Good job, Mia. So what we end up with is x equals v squared sine 2 theta over g. And this is generally referred to as the range equation.
Should we write that down?
Now, should you write it down? You know what? That's up to you. It does not show up on your equation sheet. Will you need it? Occasionally, but for what situation is it good?
Only that specific.
Only this specific problem. Launch and land at the same height. Okay?
Why is the net at the same height?
Right?
Because then you would land on the ground.
the ground.
Let's not be so.
So it's
No, the cannon's on the floor. It's all right.
No, see, this is what's going on, man. The net is like this high, you're staying on the platform.
Yeah, there you go.
So it's not on the floor.
Isn't the neck gonna bend inward and you're going to snap your neck? Yeah, it's a very strong.
Okay, we just had a car going off a cliff into some mattresses, and you didn't say nothing. And now
we did.
All right. So this is only good for a range problem. That's it. Okay? So when it comes in handy, it's awesome because it saves you a lot of work, right? But, you know, it's only good for that one type problem. So here's what I want you to do. I'm going to give you some numbers for this problem. I'm going to tell you that you're launching at 25 meters per second. Here's what I want you to figure out for me, please. In this particular problem, oh, by the way, let's say theta is 35 degrees. I want you to tell me, A, what's the range? B, what's the max height? Where's your calculator? C, what's the total time in the air? All right? So range, max height, total time in the air. Go. In the green, in the top? Ah, you mean this feet?
Yes.
That is the launch velocity. So this right here is the launch velocity. That would be the initial velocity. Not x, not y, but the velocity. Good question. All right, how we doing? We got it?
Yeah.
Okay, check with those around you. Make sure you got the same answer as everybody else.
Before we learn how to do the conservation of energy,
How do I get rid of the hiccups?
We had a question from Lauren. Lauren asked, could we use conservation of energy to figure some of this stuff out? And you certainly could. And so we're going to find that out for a lot of the things that we look at in physics. We can look at it in terms of kinematics. We can look at it in terms of forces. We can look at it in terms of energy and momentum. And sometimes there's more than one method to get to the same answer. And that's okay. So if you find energy more convenient and really,
what we can remember.
yeah, like, I don't know that energy helps you necessarily with any of these particularly, but it might.
Let's find max height of the easy for me.
Well, the problem with max height is you can't use the total velocity because since it's a vector,
Vy velocity.
you'd have to use only the y velocity.
We know V
All right, good question. On the test, if it's a standard equation, you don't have to show anything. The range equation is kind of a standard equation. Okay, so if you have it memorized, you want to write it down, that's fine. Now, I would recommend, it's not on your equation sheet, that if you would like to use it, you probably want to program it into your calculator. You know how to do that?
Yeah.
Okay, if you don't know how to do that, find someone that knows how to do it. Generally what you're doing is you just type in just type in the formula so that you see the formula. What's that?
Like store formulas.
Yeah, type in the formula and you archive it. Is that how you do it?
That'd be so neat.
Because there are different ways to do that. So what some students have done is they've taken there's a dozen or so equations that you kind of use pretty often that don't show up on the equation sheet, and they'll just type them all out in letters, one after another, and then they just save that as a archive. Is that how you do it?
Yeah, you save it as a program and you archive it so it never erases.
Oh yeah, you save it as a program, and then you archive it so it doesn't erase. That's
That's what
correct.
my sister used to do to cheat on her test.
Cheat.
Yes, on her math test.
All right, so what's our range? 59.9
Yeah.
meters, so almost 60 meters. Okay, time in the air. I would recommend that most of you probably won't memorize that equation for time in the air. This one turns out to be more convenient. But I would go V equals V naught plus GT. And I would say that the launch velocity, because remember, you got to split this thing into components, right? Would be 25 sine of 35 equals 25 sine of 35 minus 9.8 t. Is that what you did?
We did the time equation.
You did the time equation?
Yeah, it's so much easier.
Ah, whatever.
That's the
You need to know how to do this
That's
stuff.
how we
So what'd you end up with time?
2.9.
It's like the same.
2.9 seconds. Okay? All right, 2.9 seconds. And then total time in the air. That's what I did right there. I just did total time in the air, didn't I?
Yeah.
Okay, I'm sorry. Max height then. Max height, which equation? By the way, I automatically walked over here to y, because it's a y question, correct? So which equation should I use to find max height?
First one.
The first one, yeah.
This one?
Or you
Could I use this one?
You could do the bottom one as well, yeah.
I could use this one. Most students avoid the one with squares in it, but it works.
Yeah, because it's automatic.
They both have squares in it.
Yeah.
That one's just squares.
All right. I'm going to solve it with the bottom one just because.
Just name.
Vy, this is Vy at the top, right? That's going to be 0. So that's 0 equals our launch velocity, which was what? 25 times the sine of 35 minus 19.6. Where'd the 19.6 come from? Yeah, 2 times 9.8. And then this is our, whoa, wait a minute, y minus y naught. What's y naught?
0.
That's our starting position, which we'll call 0. So it'll just be y over here, correct? Or y minus y naught is the height, h. So you solve for y. What do you get for y?
10.5.
What, 10.5?
Yeah.
Does that sound right?
Yeah.
10.5 meters. A little over 30 feet, 33 feet or so. Okay? So if you could throw a ball in the air at that speed, it would go 10 meters roughly in the air, and it would go 60 meters downrange. Okay? There you go. Okay.
2.9 seconds.
What's that?
2.9.
And it would take around 3 seconds for it to land. Okay? All right, which brings us to the hardest problem of all. Okay? We'll solve it a couple different ways. Let's do the basketball problem. Okay, so here's the basketball. Let's say it's launched at 10 meters per second at an angle of 50 degrees. The distance from here to here, how far is that? 15 feet?
Yes.
18 feet? How far is it?
Wait, like
Free throw.
In real life?
Yeah, in real life, what is it?
In real life? I don't know. Let's say like 8 feet.
No!
No,
Yes,
from the free
it
throw
is.
line?
Free throw line.
No, it's not. It's like
15.
okay.
Yeah, isn't it 15 feet?
15 feet. Yeah, it is 15.
All right, so we'll say 3 meters.
Just kidding.
Okay, how high is the hoop?
10 feet.
Yeah, 10 feet.
10. So we'll call that what? How many meters?
3 and a...
Billions.
3
It's
and 1
meters.
2 meters.
2.5 meters.
I don't know.
Also 3?
Yeah.
2.5 meters.
Well, let's make it 3. Okay, let's make this 4 then.
Yeah.
All right, we'll make that 4 so they don't look the same.
That's a 3.5.
Ooh,
We got lucky.
you did get lucky. Sort of.
That means that angle is wrong. The
All right,
angle you
so
get
our
is
hoop
wrong.
is right here.
Right, the angle is wrong.
Well, we didn't say it's the right
No,
hand.
'cause they have to come back
Yeah.
down.
Now that's a 3, 4, 5 here,
Yeah.
but is that going to help us here?
Yeah,
No.
'cause it comes-
Not a bit.
I can do lunch angle.
Yeah.
Okay, so here's what I want to know is the time for the ball to get to the plane of the hoop.
How tall is the player should be?
Oh, bummer. Good point.
Short, he's a meter.
It's a turtle.
He's 0.
Leave him in the ground.
He shot a granny shot. And then
All right, let's do this then.
Just launched it.
3 meters,
How are you? 5'1.5".
4 meters,
Oh, snap.
and let's say it's a standard basketball player of about 2 meters tall.
Well, that's very...
What? 2 meters and 3 meters?
It's not the scale.
Just say 1 meter.
No,
3 foot
1 meter is like 3 feet. That's why it's like a very short one.
2 meter tall, that's a 6 foot high basketball player.
Yeah,
They're shooting.
I like this 3 foot better. It's kind of funny.
All right, so I want to know the time it takes to get to the hoop, the plane of the hoop, so the time it takes to get here, all right? And then I want to know, does it make a basket?
Wait.
Basket,
Yes, it goes.
yes or no?
Does it have to fall?
Do we have to count for the backboard?
No. All right, so here's the deal. Hey, stop, shh, listen. Does it make a basket, yes or no? If the answer is no,
How good is this player?
you gonna let me finish? All right, if the answer is no, how far above or below the basket did the ball go? No, we're going to say it shoots online. It's a two-dimensional problem. So if the answer is no, then how far above or below? Okay? There you go. It does seem complicated. Welcome to AP Physics B.
Wait.
Have a nice day.
How long are his arms? Because if you're sure, you should get
Oh, these
All right, hey, what? We've had the comment. I don't know where to begin.
Break up the components.
All right, the very first thing we always do is we break it up into components. And when we break it up into components, when you're stuck on these types of problems, there's a there's a formula for getting going. Split it up into x and y. The very first thing you do is you split this up into x and y velocity. Vx, vy, that'll be our initial y velocity. You write down what you know in the x and y, and you see which equations are going to help you out. Okay? Yeah. You could do that. You can't. You could say the starting spot is 0 and up here is 1 meter and just see if the height is 1 meter. Or you could say the starting spot is 2 and see if your ending spot is 3. It doesn't make any difference. It works either way. That's fine. We do that all the time in science, is we try to set up our coordinate system, make it easy. Hey, Rudy's brought up a good point. Rudy said, can I just chop off the bottom of this problem and have the hoop 1 meter above the ground? And the answer is sure if you want. There are a couple of ways you could do this. You could say that the initial launch position is 2, and you're going to see what this one is. And what's the condition for it to make a basket? If that's 3. But you're starting at 2, right? However, you could instead start this at 0, and then if it makes a basket, then this would be 1. Okay? So it doesn't matter which way you decide. You just need to stick with whichever way you decide. Okay? All right, to make sure we're staying on track, okay, let me just let you pause for a second. These are the only 3 things that you can possibly need to know in x. How far away it is, what's your x velocity, and what's your time. Do we know any of these?
Yeah.
Which one? 4. That's 4 meters, right? Do we know our x velocity?
Yeah.
We sure can. What will it be? Somebody have it for me?
6.4. 6.4 meters per 3.
6.4?
Yeah.
Is that correct?
Yeah.
Okay. What's our y velocity while we're over here?
7.7.
7.7. Does that sound good to everybody?
Yeah.
Okay. So we found this by using sine and cosine. So I'm going to plug that in over here. This is 6.4 meters per second. This one right here is 7.7 meters per second. All right. Hey, does anybody see immediately something we can do?
Find time.
We can find the time right here, right? Because remember, in the x direction, all we have is that x equals x naught plus v naught t, and that's 0. So we can find our time already. What's our time? 0.62 seconds. That means we can put our time down here, 0.62 seconds, because these are the same. All right. Do we know acceleration over here?
Negative 9.8.
Negative 9.8 meters per second squared. Why do we have to say negative? Because we called this positive, right? So we called the initial velocity positive, that's got to be negative, right? Okay, do we know anything else over here?
Why not is 2.
Okay, some of you are going to call this 2, some of you are going to call it 0. I don't care. It's just if you call it 2, then you're going to see how it compares to 3 over here, right? If you call it a 0, you're going to see how it compares to 1 over here. All right? So, what do we do now?
You solve.
Did you get that it goes over, right?
Yeah, over by like 1.8. 1.9.
4.8.
So what do we solve for? This y height, correct? Which equation will we use?
The first one.
Y equals y naught plus vy naught t plus 1/2 gt squared, right? We're starting at 2 plus 7.7 times 0.62 minus 4.9 times 0.62, sorry I'm running out of room, squared. And that will give us what height?
4.87.
Ooh, 4.87 meters. Now if you started this with a 0, then this would be 2.87, right? Yeah, either way it's going over by the same amount, right?
Way over.
So if we subtract the height, which is 3, it goes over by 1.87 meters. Whoa, that's a really bad shot.
He's obviously a white person.
Stop. Some of us can shoot.
Yes, your wife.
But not, yeah, my wife can, but not me.
Not forced to be last and get no food. We get the crumbs. Crumbs.
Sit there by the trash can. Open down right
Santa Claus problem?
Hey, look, a house.
Why does that have to be white?
That house is 3 stories with no windows on the first floor.
Claus isn't a Mexican last
We
name.
just call him.
It's not slide. Oh, never mind.
With an attic. With an attic. It's a big house.
All right.
12.
All right, let's say that this is, the width of the house is, I don't know, 8.
Santa Claus is very cross.
8 or 7.
All right, 8. Okay, the width of the building is 8 meters. The pitch of the roof is 45 degrees.
You're putting trees here.
Santa's at the very tippy top when Santa slips. Santa begins here with a velocity of 0.
Watch that movie now.
Yeah, isn't this a movie?
I think the reindeer.
Quiet.
Santa Claus.
All right, I want you to figure out what is the launch velocity of Santa, assuming this is a snow-covered roof that's frictionless. And then I want to know, where does Comet have to slide down and place the nice sleep number bed?
Because you know the reindeer just carry sleep.
Because it's one of the gifts in the bag. All right, so Comet flies down to save Santa. Where does he have to place the bed? At.
Bag of gifts.
So would this work for any weight?
Ooh, will it work for any weight Santa Claus? So Santa under normal weight circumstances, or Santa on his crash diet?
Yeah.
We'll find out. Okay, from here to here, everybody. Is that a kinematics problem? Or can we solve it another way?
Triangle.
From here to here. Define launch velocity. I agree. I think energy is probably our easiest way to solve for that. Because what kind of energy does Santa start with?
Gravitational.
Gravitational potential. What kind of energy does Santa have here?
Kinetic.
Kinetic only?
Plus potential, but we're going to just be.
We're going to say just lost.
Okay, if we call this height equals 0, right? Then we could say the potential between here and here gives us our kinetic here, right? Okay, you can do that. So find the launch velocity, and then find where Comet has to place the sleeping arrangements so Santa doesn't hurt himself.
Do we need to know his mass or the height of the attic or something?
I gave you the width of the building.
What about his mass?
You don't need his mass.
We don't know any of the distances on that roof.
Look, all you know is 8 meters wide, so it's 4 meters from the top of the house to the tip.
Okay,
As long as it's not a crash house.
It's a 45-45.
all right, let's do a little geometry lesson. From here to here, what's that?
8.
8. That's
Santa
45.
Claus isn't real.
What's this? 45, assuming it's a symmetric roof, right? So that would be 90. So can you find the height?
No.
Ooh, you sure can, because now this is 4, and that's 4. Oh, I just gave it away. The height that Santa slides down is 4 meters, right? So you have launch velocity. Well, you can figure launch velocity then from conservation of energy. Okay, hurry up. We don't have much time. Right. Hey, that's a really good point. What angle does Santa launch at? Because when we use conservation of energy, that doesn't give us direction.
It's just we're assuming it's at.
Yeah, we will assume that the geometry of the problem tells us that Santa will launch at 45 downward, right? What'd you get for launch velocity?
8.85.
You've got E at the top equals E at launch. And so you get mgh equals 1/2 mv squared. So the mass of Santa doesn't matter. And so your question was very valid. Does the mass matter? And the answer is no. The mass doesn't matter. And in kinematics, we know that the mass doesn't matter when you're flying through the air, right? Now, if there's drag, then mass matters. But we don't have drag, right? So we get velocity equals 2gh square root. I think you get 8 point what? 8.8?
Yeah.
8.9.
8.9.
Yeah, 8.9.
Okay, it rounds up to about 8.9 meters per second, right? That's a pretty good clip. You wouldn't want to slip on a roof like that.
Especially one with no friction.
Yeah, especially one with no friction. It's our air hockey roof with no friction. Okay, what's the first thing we do over here? Break it into components. So our launch velocity is 8.9 meters per second. We got to break it into components. When we break it into components, what do we get?
Hold on.
6 point what?
2.6 meters if we're X.
6.3-ish meters per second and 6.3-ish meters per second. Why the same?
45.
Sine.
Because it's a 45, 45, 90 triangle, right? Okay. In order to find this distance, we need the time. So how are we going to find the time? In the y direction. So here we go. Since we're running out of time for ourselves, y equals y naught plus vy naught t plus 1/2 gt squared. Where do we launch from? 12. Where do we land? 0. What's our initial velocity?
6.3.
No!
One going.
Negative 6.3. Oh, bummer. Negative 6.3, right? Because it's down. Okay?
Minus.
Okay, minus 4.9 t squared. Oh, danger, danger.
Stranger danger.
What do we do now?
T.
Solve for t. How?
Put it in the calculator and find it.
No, you can just, what you meant to call it.
Yeah, t equals in a number, right?
Yeah.
How do we solve this?
Calculator.
Oh, you don't want to factor that? Bad, bad.
Put it into that one.
Put it in your calculator, and your magic calculator solves it for you.
Yeah.
Put it in the Y89, gosh.
Okay, if you have a TI-89, it will solve it for you. If you don't have a TI-89, how do you solve it?
That one
Put it
equation.
into Y equals and then
Yeah, but
No,
find
no,
where
no.
T find where it intercepts the T.
Okay, here's the deal.
Y equals
You could use the quadratic formula, correct?
Yes.
Which would be B
Equals.
B plus or minus
Square root of
4AB.
4AC.
4AC, that's what I meant.
4AC.
Plus.
Over
The negative B here?
2AB. 2A.
AB something.
Is this positive or negative?
Negative.
It's negative, right? Negative B plus or minus 4 square root of 4AC over 2A. Okay, R. Hey, stop. We're not done. Sit. Don't rob me in my last 2 minutes. Okay, now.
Equations wrong. B
What?
squared minus 4AC.
Oh, B squared. There we go.
No.
Under the radical, B squared minus 4AC. Yeah.
Okay, go.
I don't think there's a negative sign.
That looks stupid.
Yes, the negative
Yeah,
sign
that's
there.
it.
Negative B.
Yeah, that's it there.
Now that's.
I'd still just put it in the calculator.
Is that right?
Just move to the next one. and find
Okay.
the y-intercept.
Since it appears that we have trouble remembering what the quadratic formula is, are other ways to do this. In your calculator, you'll put y equals this. But this has to be 0 here, right? Y equals this. You'll graph it. And when you graph it, it's going to be a parabola downward. Why downward?
Because it's negative.
Negative t squared component, right? And you're going to find that root. And when you find that root, that's your time. Okay? And I think for most of us, graphing it and finding the root is by far the fastest way. Unless you have a TI-89, and then you can just plug it in and have it find the roots for you. Okay? All right, that's it. Don't forget, Archery of Doom is due Wednesday. We have e-homework tonight. We also have e-homework Wednesday night. The Wednesday night homework we have covered. We are through with trajectory motion. We're going to start in this momentum on Wednesday.
Momentum, yes. Something I understood last year.